Okay.
And I don't think we should
Now I want to say something like that. Very good.
better throw this
Okay, so let me start. Okay, so just let me know, are there some second and third years? I mean, yeah, I know. Okay.
Yes.
Abhinav is in eighth year. They are in fourth year, right? So, hello, what did you guys say? Hello. Hello.
Yeah. You're audible.
Okay.
सामने से कोई नहीं बोल रहा.
Okay, so someone just.
Yeah, you are audible. I mean, please try to speak a bit too loud. I mean, our audience is not that good right now.
Okay. So I just wanted to ask: are there second and third year students in the audience, in the combined pool of audience?
Yeah, second years are there. Third years I think are also here. Yes.
Okay, fine. Then the talk would.
Yeah, there is one second year in LH4.
Okay, very good.
Two second years are there in LH4.
Okay, that was so encouraging. Very good, Divya. Okay, let's start. Okay, so
6 people in 514.
Fine, let it be whatever. Okay. So yeah, so you know the topic already. We had so good evening. I think yeah. So there are only few second, third years. Then they might not know me. So I'm Pulkit, and I'm currently working in MESA Institute, Chennai. And yeah, I'm currently working on a different project, which I'll talk about later. But for past more than 1 year, I have been working on these X-ray binaries, and I have used this. So when anyone says to you X-ray binaries and MESA, so X-ray binaries must ring a bell. If you have any degree of astronomical inclination in your interest, it must ring a bell. It's like, you know, you have heard binary systems, so you might imagine that, okay, this is a binary star system, and then there is X-ray, so you might imagine that it might be producing X-rays, or it might be observing X-rays, or something related to observation in X-rays. Okay, but MESA might not ring a bell, and a significant part of this talk will be focused on those systems. What is MESA, and how to use it, and what's its significance. Okay, yeah. So with this, I move forward. What is happening? Ooh. Hello guys, can you see my screen? Is my internet stable? Hello?
Yeah, we can see. You can just hide that bar.
Okay, fine. I can hide that bar. Yeah. So, okay, whenever I ask something, just someone be there to monitor. Otherwise, I'll feel like I'm talking to this computer, sitting in a very large hall alone. That's scary. Anyways, so yeah, first a few minutes I'll spend on binary stars. Then I'll move on to talking about X-ray binaries, which is the topic. So we need some properties of basic binary interaction. What are they? To just warm up to know about X-ray binaries, and then I'll talk about MESA, and then opportunities, the scope. So this fourth section will depend upon your interest and what do you want to know about working in these areas. Whatever your questions will be, I'll be happy to answer. Okay. So yeah, with this precinct, let's start with just getting a sip of water. Okay. So what do we mean by binary stars? Simple. There are two systems, there are two stars. I mean, any two objects revolving around each other, around a common center of mass, can be said a binary system. For simplicity, a very unusual example, unusual but apparent example would be Jupiter and Sun. So the mass of Jupiter is high enough that the Sun and Jupiter's common center of mass lies just outside the Sun, and it can be said that they are a binary system. But then, of course, you know that Jupiter is not a star, and there are other planets as well. So solar system remains pretty much stable. But then if you talk about binary star systems, then there are so many. So here is one of the points that I've written. How many binaries are there? Oh, sorry. Okay. So for this, some of you might be surprised to know that most of the targets, by targets I mean, whenever you take out your telescope and or join astronomy club observation session, then most of the pinpoint light sources in the sky which you see are in fact binaries. Okay, and some of them are also triple star systems, and some of them are 4-star systems as well. If I might be wrong about a few names because I have been out of touch. I am not in NISER. Sorry about that. So, but if you observe one of the most common evening stars, that is Algol and Midjar, I think they are a four star. Their system of 4 stars orbiting common center of mass. So yeah, so there are so many binaries, more than 85% of the pinpoint sources in the night sky. Okay, so this being established, there are of course, you can divide them on the basis of their different kinds of properties. For example, if you divide them on the basis of observational properties, then you will get some categories which I will discuss in just a minute. Before that, I just want to draw your attention to this diagram. So this is a standard schematic diagram. Just a few highlights to catch the basics that here are 2 stars, and in center at this cross mark is the center of mass of this system. So although it's mentioned, you can guess that, I mean, not guess, you can conclude that this star would be of higher mass because it's closer to the center of mass. And both of these stars have some kind of elliptical orbit, although one of this looks circular, the bigger one, but that's not the case. I mean, we can't say that stellar systems have very high ellipticity. Most of the ellipticities are like 0.003, so they're 0.005 or 0.01, so they're almost circles, but not fully circle. Okay, so one very common example of a binary system is Sirius. So had I been giving this talk physically, I would have asked people, have you seen Sirius? And so many of them who would have attended the astronomy sessions and all, they might have raised their hands, but nevertheless, constraints of being distant. Sorry, are you, is someone saying something? Yeah, Abhinav raising your hand, sorry. Hello, okay. Should I proceed? Okay, fine. Okay, so yeah, here is the Sirius system. So yeah, from this star, you can just check whether, in which part of the sky is it visible. So there are 2 stars, Sirius A and Sirius B. Of course, this is a so much zoomed out picture. I mean, with naked eye, you can't see both the stars to be separate. In fact, with powerful telescopes also, I don't know. But this system has been one of the very important binary targets because Sirius B is a white dwarf star, okay? And this was the first system in which people encountered one of the compact objects and or stellar remnant, and which turned out to be white dwarf. So astronomers who measured all the astrometric properties back then were baffled because they could not believe that such a huge amount of matter can be constrained in such low volume, which is there in the white dwarf. So then they had no idea of the existence of such degenerate matter stars. Okay, so that's why this system is important. And Sirius A is just a spectral A1 spectral type. By MS, I mean main sequence star. It has the mass of 2 point something solar mass. So yeah, it is still evolving. It has not reached its giant branch phase. That okay. So yeah, as I said that I have few links. Yeah, I have this link here. I've kept it open. So let's discuss, before moving forward, let's discuss about a little bit of properties of binaries. Okay. So can you see this screen? I mean, Australia National Telescope, National Facility, whatever. You can see it's fine. Okay. Okay. So yeah, there's some binaries which can be distinguished using a telescope. So one of the example is, yeah, this alpha cane A. I mean, Alpha Centauri A and alpha. So this is a close. I mean, this star is one of the closest to our systems. So yeah, here you can check. You can easily distinguish them. So it's easy to classify as a binary. Okay. Then there are these spectroscopic binaries. Okay. So yeah, these systems are also important in the sense that, say you use some telescope, say Hubble telescope, and you point to some distant pinpoint source, and zooming enough, you are able to find that okay, you can be I mean, the system is a binary system. Okay, so how will you detect the properties? How will you detect that at what speed are they revolving around each other, or at what speed are they spinning, or how much mass do these components individually have? So for these data, to get these data, we use the Doppler shifting that happens due to their binary motion. Okay, so compared to a stellar system, so say there's a single star system that is, so that will just have some peculiar velocity, say some linear velocity. Okay, apart from the cosmological redshift at its location, so you will just get one Doppler shift. But if there is a binary system, then you will get different Doppler shifting. If anyone is not is finding this concept of Doppler shifting, how is it used, then they can just stop me and I'll explain. Okay, so currently I'm just moving forward. Okay. So yeah, you can use this Doppler shifting due to their motion around each other to know the phases or the positions of the binary components. Okay, and you can know their distance from each other, which is an important evolution parameter. That distance will tell you the binary orbital period using Kepler's laws, and then you can know the masses of individual components. Okay, so this is how we get those data. Yeah. So basically, all the observational properties are recorded. Then there are eclipsing binaries. Okay, so eclipsing means that these binary have generally so a lot of people work in exoplanets. So one of the most famous methods to detect exoplanets is transit method. So these are similar systems. So say there is one star and one big planet revolving around it. Then if the planet will come in front of that star, the luminosity of the star will dip. Okay, just because you are in the shadow region. So that luminosity can be plotted, and based on the periodic variation in that luminosity, you can detect the properties of these binaries. Okay, so I gave an example of star-planet system, but of course there can be two stars. There can be systems, X-ray systems, which I'll discuss further. Like say a very big red giant is in a binary system with a neutron star. Okay, so those systems can be observed. And then, yeah, so here are some graphs given. That's how eclipsing happens. And I mean, if you're interested, I'll give you a link to a very famous review paper written by Bhattacharya and Yuval in 1991. So if anyone starts any research about binary systems, that review paper is considered like a Bible. It's given to everyone who starts their study of binary astrophysics. So even though the paper is 30 years old now, it was published in 91. So yeah, you must read it if you want to study, go into astrophysics. Okay. Yeah. Then there is astrometric binaries. Okay. So yeah, these binaries show a different kind of wobbling motion. That is because they have. Yeah. That is because they have. Okay. How can I explain? I mean, yeah, that wobble or perturbation is there because you can, I mean, it appears so. It is not actually happening. It appears so because you can only okay, I'll give the example. So when Sirius A was discovered, people didn't know that it was binary. People just knew that its motion is showing such kind of wobbling, and then they concluded that this wobbling is happening due to the presence of this white dwarf as a binary component. Okay. And then there will be exotic objects. Okay. So exotic objects includes all kind of gravitational wave sources such as neutron star binaries and X-ray binaries and all. So in this talk we'll study one of them. Okay. One broad category of them, that is X-ray binaries. Okay, so going back to slides. Yeah, can you see the slides? Is it fine? Hello? Hello? Someone respond, please.
Yeah.
Yeah, please respond if.
Yeah, hello?
Yeah.
Am I audible?
Yes.
Yes. The slides are moving. It's fine. Please go ahead.
Keep responding because internet remains pretty unstable in this institute. Anyways, so now let's talk about binary interactions. So what do we mean by interaction? There can be so many interactions. For example, if you keep two charges, so if you keep two charges close to each other, they will exert gravitational forces on each other. They will exert electromagnetic forces to each other. Depending on their distance, they can exert like nuclear forces also. But for astrophysical purposes, most of the the major dominant role is played by gravitation in the interaction. Okay, so what happens due to gravity? So when two objects come closer to each other due to this gravitational attraction, yes, something might have just a linear velocity and it can fall in the gravity of another object. That can also happen. So first, tidal disruption will happen. What do we mean by tidal disruption? So then for those of you who don't understand, so say moon is closer, the most basic example is Earth-Moon system. So moon is closer to Earth, close enough to Earth. So then moon is able to influence the fluid component of Earth's crust. And that fluid keeps moving from here to there on the Earth's surface itself, but it remains bound to the Earth's surface, okay? And that motion causes tides. So that is known as tidal disruption. If it happens to an extent that the whole body is not able to remain its spherical shape, then things will move forward, and it happens in a lot of cases. So just imagine the Earth-Moon system and they replace the moon with a neutron star. Then what will happen? Even the solid part of Earth's crust and mantle would not be able to hold them on the Earth's surface, okay? And then it can get totally disrupted and mass transfer can happen and different things can happen. So to understand them, see, at this point, technically, there will be a lot of equations, but I have tried my best to remove all the equations in this talk. So I'll just give you an overview of what is happening. So at that point, so to understand this interaction, we use gravitational equipotential curves. So what are these? In simple languages, if you can see this figure, there are two objects, M1, M2. Somewhere here is their center of mass. It's very close to M1. That's fine. Okay. So, and these have a common omega to orbit around each other. Then, at any point, say at this L5, you can write the gravitational potential of this system. There, you know the distance from M1, from M2, and you also know the distance from the common center of mass. Okay, you also know the distance between them. So you can write, and you also know the omega because you have observed all these properties. Okay, so you can simply write the gravitational potential due to these systems at this point, at any point. Okay, and then you can plot the equipotential curve, which anyone has done in their CM course or EM courses. Okay, now one of the curves is very much important, and that curve is this one, the 8-shaped figure, which you can see here. I mean, there's an 8-shaped figure, okay, and you can see the M2 is completely filling that curve, okay. So this curve in 3D is known as Rochelot, okay, and it's a very important curve. Okay, I'm sorry, I should have taken a good picture. Therefore, I'll just try to open. Yeah, can you see? If you can see this slide now, so here you can see that M2 and M1 are stars. There is the common center of mass C, and there is this 8-shaped lobe. In 3D, it is known as a lobe. Of course, in 3D, imagine electronic orbitals, p orbital. So that way, that is also similar shape, right? So that way you can imagine that in 3D it will be a lobe, okay? So, and both the stars are inside their Rochelot, okay? Why is Rochelot important? Because any material which will go out of the Rochelot will be free from the influence of the gravity of M1. Say if the material goes out of here somewhere, okay, then anything can happen to the material. So it is no longer bound to M1, okay. So it can get accreted to M2, that's fine. It can just get inside the Rochelot of M2 and be orbiting M2. It can start orbiting M1 also. And it can also be really far from the system and be in a common orbit around M1 and M2, okay. So yeah, let me go back to those slides. Yeah. So now what happens that any star keeps keeps expanding during their evolution. Okay, why? So if someone has this doubt, then let me clear it right now. That what happens? So why do stars expand? Simple reason would be that the rate of energy generation in the core is much higher than the rate at which energy is escaping the star. Okay, and this makes a lot of heat dumped into its envelopes, which heats up the gas. So what are stars made up of? Just gases in the plasmic form. Okay, because of high temperature, the gas remains in plasma format, and it cannot remain in plasma format also. That's fine. But what happens is, unless the energy is being generated in neutrino format, which does not interact with matter, unless that happens, and that only happens at very extreme cases like supernova explosion. So unless that happens, energy is generated in terms of photons, and you must be knowing this common astrophysics fact that any photon which is, say, the example of sun, that any photon that is produced at the core takes about 5,000 years to come to the surface and get eventually radiated. Why? Because its path is not linear. It keeps on random walking, colliding with all the molecules in the plasma. Okay, so all that collision dumps a lot of heat, which makes the star expand, and whenever due to that expansion the material gets out of the Rochelot, it can be transferred or just lost, or as I said, it can be in a orbit, in a common orbit or common envelope around both the stars. Okay, so yeah, this is a very rough overview of binary interaction. So a lot of things happen when the material gets out of the Rosselló. The flow of matter can be stable. It can be unstable also, in which case there will be a common envelope. In the stable case, an accretion disk can form. Okay, so we'll see those things as talk proceeds. Okay, now I finally come to the topic. So, X-ray binaries. So why are some binaries called X-rays? Simply because they appear in X-rays. Okay, when you have, so if you see this picture, I like this picture very much because it's an artist's imagination of a special kind of X-ray binary, which shows what will we get when we have a multi-messenger observation of any binary system. So what do I mean by multi-messenger? It's simply a new way of astrophysics that has emerged due to the availability of so many telescopes. Take a point source. If it is interesting enough, observe it in all the available windows of EMS spectrum. So what will happen? As you can see, this star opticals, this star appears in optical or infrared. Then there is X-ray heating here, and these binaries are termed as X-ray binaries because you see there's a jet here, and that jet is produced due to accretion. I mean the material which actually gets accreted. So yeah, okay, just hold on. Just let me first introduce some terms. So of course this component, so here there are two components. One is this star, and you can see that it is already filling its Rosselló. That's why it has this teardrop shape instead of being spherical. Okay, and what is so okay? I missed a very key fact in the Rosselló picture. So it is losing its mass from here. Okay, from this point. And if I go to the previous slide, this point is L1 point, and you all must have seen today that Aditya is being launched to study sun, and it will be placed at L1 point. That is the Lagrange point 1 of Earth-Sun system. So why are we placing it on L1? Because of two reasons. On L1 it can be stable. Okay, it can be in a very small orbit here and just rotating. I mean, yeah, practically stable for the purpose of study of sun. And if it is at L1, we can just keep looking at the sun throughout the time. I mean, they're unaffected by seasons or the position of any other planet in the solar system. Okay, so for example, if you have to, of course, while explaining this, I'm considering that M2 is sun and M1 is Earth. So say if you have to put a satellite to observe the other planets of the solar system, then where will you put? At L3, because you can view them without the interference of sunlight. Okay. Similarly, if you have to observe something on the other side of the sun, you will put them at L3. So that's why these Lagrange points are important. Okay. What happens in these binaries, that these points become the zone from which matter is leaked. So a leak from an expanding Rosselló filling component, and that matter forms an accretion disk around the compact object, around the stellar remnant component of the binary, and the accretion has not happened yet. So accretion disk is being formed, and the X-ray or gamma ray pulses or bursts are only generated when in the center of this disk, where the compact object is actually situated, this material interacts with the magnetic field of that object and gets finally accreted to that object. Okay, so if you are not familiar with this process of accretion, let me just clarify that if a satellite is rotating very crude example. I'm sorry about that, but I think it's the easiest to understand. So if a satellite is rotating around Earth in an orbit, it will be just like accretion disk. Okay, accretion disks. The material in accretion disk are also revolving around that object because the centrifugal force is being balanced with the gravitational attraction, just like a satellite. But if satellite falls on Earth, that's accretion. Okay, so when I mean, similar situation here would be that this material is actually getting dumped as the mass of that particular object. Okay, so and in that process, X-ray is emitted. Okay, that's why we call these systems as X-ray binaries. An example would be neutron star accretor main sequence donor or a black hole accretor main sequence donor. Okay, generally one of them is a compact object because because their gravity is high. But then I have a question that why not white dwarf accretors? So the answer to that would be that the X-rays will only, the gravitational potential loss of the material which is infalling to the to the compact object. Wait, is my video off? I'll just switch it on. Why am I off? Video is stupendous. Sorry. Yeah, so let's continue. Sorry about that. Okay, so the white dwarf accretors are not a part of X-ray binary systems because the X-rays are only produced when the gravitational potential energy loss of the infalling matter should be high enough. Should be high enough that the pulses which are produced lie in the X-ray range. Otherwise, they will just be optical or ultraviolet. So, and that won't be so distinct. Okay. So with this thing, I proceed to classification. Okay. So now we know what are binaries, how do they interact, and now we know about this special kind of binaries, which are X-ray binaries, which have a main sequence donor and a compact object as their accretor, preferably a neutron star or a black hole. Okay. Now we'll move on to classify. So of course there are various categories which you can use to classify, such as astrometric categories which I showed you earlier. But we choose to classify them on the basis of the mass ratio of the donor and the accretor. Okay, if some of you might be wondering why do we choose mass, then let me tell you. If you're aware of, okay, I'll show you a picture here. This is, can you see this stellar life cycle picture? Please, someone just say yes or no.
Yeah.
Thanks. Okay, so if you see this picture, then there are two possible trajectories of stellar evolution. So one is when the star has greater mass than 8 solar masses, one when it's lower than 8 solar masses. So you see that the point, I'm not going through all this category, but the point to observe here is that the mass of the initial gas, the gas which starts hydrogen burning, so the mass of that gas is the only important component which will decide the trajectory of evolution of the star. Okay, so that's why we choose to classify our systems on the basis of mass ratio of donor versus accretor. Okay, so low mass X-ray binaries has mass ratio close to 1, and high mass has ratio very high, let's say 20, 25. It can be 200 also, but we have not observed any such numbers. Okay, so now if I consider a compact object to be a neutron star, then so neutron stars have fixed mass. Okay, 1.35, 1.4 solar masses. The maximum mass of a neutron star that has been observed is 1.97. So Oppenheimer actually estimated it to be 2.3, 2.4, but then he was wrong. He was slightly wrong, and then 1.95 has been the maximum. Okay, so yeah, considering that the donor has mass 1 or 2 solar masses for low mass X-ray binaries, and for high mass X-ray binaries, donor has say 10 or 20 solar masses. So it's nothing like This is a hard classification, or we have not found any systems whose donor mass lie between these range. We have found, but their way of evolution is not so clear to us as these categories are clear. Okay. Okay, so with this introduction to HMXP and LMXP, let me explain what are they, how are they. Okay, so can anyone guess which system is this one? I mean, it's obviously an X-ray binary because this is companion star is expanding, filling its dorsal lobe, and accretion disk is there. You can get accretion X-ray from this jet, but if you can guess or otherwise, I'll tell you. Okay, see, these are the perks that you enjoy in an offline talk. But anyways, so I know.
Yeah, that's very true.
Yeah, I know that this is a low mass X-ray binary system. How do we estimate that? For that, let me go to the difference part. Okay, so these systems have different mass transfer mechanisms. Okay, so so what happens in high mass X-ray binaries? Generally, the initial donor star has like mass in the range of 10 to 20 solar masses. So they are like what do I say? They're giants, okay, and they evolve like giants. So by that statement, I mean that you must be knowing this, that the star, if a star is massive, then it will evolve faster because its gravitational, self-gravity will be higher, which it has to counteract through nuclear fusion. So it will burn fuel at a high rate. Okay, so it will evolve faster and it will also expand faster. And when it will expand, it will quickly get out of its dorsal lobe. And when it's also when it's crossing the dorsal lobe, the material at its surface will be free from the gravity of the core. Okay, so that material will be ejected like this, ejected spherically in the form of wind. Okay, and this in practical examples, some of which I have simulated, these winds are so high that this small dot is a neutron star. This diagram is not entirely correct. This diagram, I found this diagram in the Theoretical Astrophysics Volume 2 by Padmanabhan, which is standard book of astrophysics, but these systems are so dominating that even from this side, the opposite side of the neutron star, there is significant enough mass transfer. Okay, but in low mass X-ray binaries, you can just say कि इसका कुछ औकात नहीं है. Okay, so it will evolve very slowly and it will fill its dorsal lobe in quite a long range of time. And when it will fill, it will not fill such dominantly, in the sense that the rate of expansion is not that high. So it will just start leaking its mass from the L1 point, because at this point, after this point, the gravity of the second star dominates. So, and in this case, the accretion disk will form. So, after understanding this, you can tell me that this is a low mass X-ray binary system, because otherwise there would have been a giant star here, and there would be wind-fed accretion mechanism, okay, instead of disk-fed. So there are two kinds of accretion. One is through building this accretion disk, and the other is through spherical accretion, which is wind-fed. Okay. There are other kinds of interactions also. These are not the only two kinds. Okay. If someone comes to me like there is Bondi-Hoyle accretion, you do not talk, I am not responsible. Okay. I mean, yeah, people have a lot of objection on these classifications of accretion types, because there are a lot of systems which have not been understood yet. Okay. So now how does this accretion affect the observation of those systems? So the most important point is that in these high mass systems, the rate of accretion is so high. I mean, it's regularly, it's consistently high for a long period of time. So say, okay, and I am not sure about these numbers because these are just the estimates that I have gained through my experience. So a typical age of X-ray binary is about 1 billion years, okay, 10^9 years, okay. And in that portion, this phenomena of accretion disk happening, and not just the disk formation, this releasing mass phenomena happens for a very short period of time, of a few million years, say first 10 million, 20 million years, okay. When the accretion rate is high, by high I mean 10⁻⁷ to 10⁻⁹ solar masses per year, okay. Please keep this number in mind. Now, high mass X-ray binaries have the same rate of accretion, like greater than 10⁻⁷ solar masses per year, for about 50 or 60 million years, and that's a quite high portion of the evolution age, okay. After, what happens in LMXPs is that when their accretion rate falls below this 10⁻⁹ solar masses per year, below 10⁻⁻10, then they become transient in nature, okay. So, okay, to explain this better, let me go to this diagram and just take me some water. Yeah. So, okay. So, this is a low mass X-ray binary system. So, what happens actually? So, accretion is happening here, but this accretion is very low. Okay, for a very brief initial phase, this accretion is very low, and the material is already there in accretion disk, and it's not coming here, from here. I mean, the accretion disk is not being continuously fed by matter. So, I mean, how will we get X-ray due to accretion there in that case, in such a case? So the answer is that this disk becomes so hot that it is both thermally and viscously, meaning due to friction in between the layers of the disk, it becomes unstable, and nuclear fusion happens here also in the disk itself. And then when the pressure is high, this disk, the inner portion of that disk interact with the magnetic field of the neutron star inside, and then they get accreted. So it's like there is no accretion for a long time, and then there is suddenly the disk becomes unstable, and there is a law. I mean, there's a good amount of accretion. Then again, the LMXV will be silent for say 20 years. Then again, five months it has very good accretion. Then again silent for say 50 years or 100 years. But in high mass, so this is what happens in LMXV. If anyone has doubt, please stop me right now. But what happens in high mass X-ray binaries is that it keeps the material is continuously fed to the accretion disk, and from the disk it is continuously being accreted to the compact object like a stable phenomenon. Okay, so based on that, what we get to observe is regular pulsations in high mass X-ray binaries, HMXVs, and irregular bursts in LMXV. See this. So left side is your HMXV. It's like regular pulses, not so regular, but okay, mostly. And right hand side is a low mass system, just showing an X-ray burst. Okay, so yeah. And by the way, oh no, I can discuss that point later. Okay, so this is how we differentiate. Okay, now. So I'm done with the differences. If anyone has anything to point out right now, otherwise I will explain this evolutionary example. So at the end of all this, after this I will move on to demonstrate the modeling. But after all this jargon, I just wanted to give you an example of just an ordinary case of two stars in a binary system. Okay, and this example is not, I mean, of course it's not the only possible trajectory. There can be many trajectories. Okay, people are still learning these things. By people I mean the astrophysics community, and we are not sure of all the phenomena that goes in. For example, Luxor is still trying to understand what happens in a common envelope phase. Okay, so here, if you can see, I'm sorry that I could not find a better diagram. There's no better diagram available. This, I should thank Abha that she had this book with by Ivanova and Ricker. That is a really important textbook. So in that diagram, this schematics were drawn. So here there is in the left side where my pointer is, there are two stars, 2.3 and 1.m solar masses. Okay. So what happens? The massive one expands first because it evolves faster. Okay, it overflows its Roche-Lobe, and then there is a stable Roche-Lobe overflow. Mass gets transferred to the another component. Okay, then there is this system. So what has happened that in the leftmost star, only the core has remained. The core has already become a white dwarf. Okay, because the initial mass of the star was less than 3 solar masses, so it has become a white dwarf. All of the envelope material has been transferred to the other star. Then this is 3.4, okay, solar mass. This will expand like a high mass exoplanet. This will start expanding, and when this will form a Roche-Lobe, it will be unstable. Okay, now what happens in an unstable Roche-Lobe overflow, that the rate at which this star loses the envelope matter is very high compared to the rate at which this small compact object is able to accrete or able to form an accretion disk. Okay, so this is the case of high mass exoplanet. So due to unstable overflow, it forms a common envelope. Common envelope meaning that all the envelope material of this star lies in the orbit common to both of the stars. Okay, so you must remember that earlier I had explained you while showing the Roche-Lobe diagram that if the material is lost, it can very well go into a common orbit around both of the stars. It's not necessary. I mean, it's a common misconception that happens that if a material is lost from donor, it will go to the accretor. No, it can very well form a common envelope phase. And so what is the scenario? So this object is white dwarf, and this object is also white dwarf, but it has some helium left here, which can burn. Still, some nuclear fusion in cells can go on. Now, what will happen? So there are two possible scenarios. Either both of the white dwarfs will merge, they will form a neutron star, and they will have this envelope around them. So this condition is known as Thorne-Zhidkov objects, and I'll explain it a little further. But these are a very unique objects upon which I have currently started working on. And yeah, if you check the other case, if the merger is such violent that some explosion happens, I mean, I'm not sure if I can call it a supernova, but such explosion happens that the shocks are able to eject the envelope material in space, then it will just be a white dwarf plus a helium burning degenerate core. It can merge. It can just so some mass transfer will happen because it has some material left, some normal material left. By normal material, I mean the material which is not degenerate yet. If you know, these white dwarfs and I mean, for those of you who don't know, white dwarfs and neutron stars, these compact stellar remnants are made up of degenerate matter, the matter which is only stable because of the degeneracy pressure of fermions. Okay, so no more nuclear fusion is going on, so that degeneracy pressure is able to withstand the self-gravity of the system. Okay, so then these compact objects will be a gravitational wave source here, and then they can merge and they can form a neutron star, they can form a big white dwarf, anything can happen. If you check this case now, the rightmost case, there are two stars, and say they have masses high enough so that both will evolve to a neutron star. Then what will happen? So the high mass will evolve first, the core will become a neutron star, and the envelope will be transferred to the other star. There will be a supernova here, of course. Then only the envelope will be completely lost to the other star. Then the other star will be massive enough, then it will also go through the same phase, and then there will be another supernova or common envelopes, okay? Because this is now an high mass star, okay? Then it can, then there are two cores, both are neutron star cores, so they can eject the envelope or they cannot eject the envelope. A lot of things have happened. So this question mark signifies that so here we don't know. We don't know what exact physics would happen. We don't know what criteria should be provided. For example, in a stellar evolution, we know that if the initial mass is greater than 3 solar masses, it will become a neutron star, or it will become a void dwarf. We know that. Here we don't know. So that's why this question mark has been put. And then another supernova might happen. So this will also become a gravitational wave source, and then the LIGO Virgo will detect it. Okay. So now, this is say something.
So, sorry if I missed it. So, why would the common envelope be ejected into the space?
No, it's not necessary that it will be ejected, but say there are two systems, and this. Just give me a minute. Yeah. So there are two systems, and these two compact object systems, they are revolving around each other. So they can merge and eject the envelope. That is one scenario. It can also happen that this ejection is happening due to the nuclear fusion going in the shell of the right component. So these are the two reasons that I know. Okay. Hello.
So the second reason is nuclear fission going on, or
no nuclear fusion and going on in the shell of this core.
All right. Okay.
Okay, so that's fine. It is also possible that this core. So basically.
Sorry to interrupt, but it could also happen they are still binary when they are in a common envelope, right? So maybe they are gaining some angular momentum, and that energy is being transferred onto the envelope, and that is being ejected into the space.
That happens. That actually happens. Okay, I was gonna say it. Okay, you said it very good. So that happens, and the mechanism is very similar to what happens in a supernova explosion. So there also the envelope is ejected. Here also the envelope is ejected. And as you rightly pointed out, very much right, that the angular momentum is the key factor. Okay, if the angular momentum is not powerful enough, then it will form a Thorne-Zitkov objects. Otherwise, it can get ejected. Yeah, very good.
Right.
Okay, so I'll move forward. So I think we have already discussed something about. So why do we need to study X-ray binaries? So first of all, they are progenitors of so many exotic objects. Exotic meaning the gravitational wave merger objects like neutron star system. Divya, here you asked that ejection can also happen. So I just want to add that here it's a very much possible chance, because what happens that this envelope, so it's a core, right? And the core is a compact object, right? So the gravity is powerful enough, the gravity of the core. Okay, so this material has a gravitational pressure of getting accreted to this core, okay, to this helium burning core, and that this accretion is different from the accretion which I described in the previous slides, in the sense that this accretion is super Eddington. So some of you might not be aware of the Eddington limits of accretion. So what happens in that there is a certain so when any material is falling to the accretion disk of any compact object, there is a certain radiation pressure due to the material already present there, which is very hot. So the radiation pressure is trying to not invite additional matter, but the gravitational pull of the object is trying to accrete additional matter. So these two are in competition, and when these two are balanced, that is known as Eddington's limit of accretion. So beyond that, there is no accretion. I mean, the accretion, that is the maximum rate of accretion that can happen. But here in the common envelope case, the accretion is always super Eddington. Okay, and it happens that this material is entirely accreted to the core in such a short amount of time that it gets ejected due to the shock wave that is produced. Okay.
Okay, right, that makes sense. Okay.
Yeah. So this happens. So if you're interested, I can give you a paper about classical formation channel of TZOs from high mass X-ray binaries. There it has been described clearly.
Okay, sure. I'll be happy to take that reference. But if other people's needed, maybe we can send them via email also.
Okay, sorry. Of course, Tanya, you can check it out yourself also. I mean, it's written by Philip Podolsky, and that is one of the most famous guy. He's in Oxford. He has worked on all kind of binaries. He has worked on TZOs, and he's now working in gravitational waves also.
Okay.
He's a giant. You can write to him for PhD. Anyways, so the question is, how do we know their evolutionary stages? So we know them because, say for low mass X-ray binaries, we have observed like more than 500 in our nearby galaxies. Okay, and we have observed all of them at different phases in their evolution. Okay, so now a lot of theoretical astrophysicists have worked and have simulated a lot of such cases. Okay, and they have joined all the dots the dots which have come from observations of different LMXBs at different phases in their evolution, and then this picture has been able to be produced. So what you are seeing is a very hard work of past 100 years. Yeah. So yeah, and how do we know what to observe and how? Yeah, I think I have already answered this question because I have already explained how do we take astrometric data and how do we identify systems. So that's fine. The third and most important question is, how do we build a model? Okay, so we have different data for, we have observed the systems at different phases. Now we must simulate them so that we can link, okay, so this object has come from here and this has come from here. For example, we come to this slide that why do we study X-ray binaries? Okay, so because they're progenitors of these exotic objects. So I was gonna talk that one such exotic object is this Thorne-Zitkov objects. So what happens if the common envelope is not ejected? There is this giant star which is being formed, and it looks like a usual red giant star. Okay, but if you can detect it, the core inside that star is a degenerate core. It can be a white dwarf, it can be a neutron star. Okay, and it was proposed by Kip Thorne and Anna Zitkov. So that's known as Thorne-Zitkov object. Yeah, it's the same Kip Thorne, the GW person. Okay, so yeah, so far we have detected a few sources, but we have not been fully confident that okay, these are Thorne-Zitkov objects and not usual red giants. But yeah, my job is to find out some observational properties, like simulate and find out some observational properties. So let's see. Anyways, so and yeah, the LMXBs are also sources of millisecond pulsars, which are very precise atomic clocks. So you must be knowing about pulsars. Any neutron star with a magnetic field which is inclined at some, the axis of the magnetic field. For example, take Earth. Earth is a mere planet, but the magnetic field axis is not the same as its rotational axis. Okay, So when this happens in a neutron star, they appear to us as pulsars. Okay, because you can look about go to internet, look about pulsars, look the contribution of Jocelyn C. Bell. She is very important. And yeah, and millisecond pulsars are the pulsars which have their spin periods in millisecond. Is like 0.007 millisecond. So they revolve with such precision that it has been an international debate in recent days that people are asking to recalibrate our atomic clocks using these pulsars. And these pulsars are also important, very, very much important for the pulsar timing array collaboration, which is trying to detect. So recently there was a famous announcement. We invited Manjari for talk also, and I'm currently working under her. So PTA people are using these millisecond pulsars, which emit in radio, so radio millisecond pulsars, to study the nanohertz gravitational waves, and those are very important. Those are like sometimes I think they are more important than the other GW sources, like the fourth point, the formation of compact binaries GW sources. So there are two kinds of gravitational waves famous these days. One is low frequency, one is high frequency. So in high frequency, we get to observe by LIGO and Virgo by the collision. So those which are produced on the collision of black holes or neutron stars, such mergers. But using these low frequency gravitational waves, so to give you an idea, these high frequency gravitational waves have a wavelength of kilometers or something, but a football field in American terms. But low frequency gravitational waves have a wavelength of light years, and they can revolutionize our understanding of the formation of universe. So currently you must be aware that JWST is there in space, and it has pointed out that something which is people are saying that the cosmology should be revived, it's not correct, and blah blah. So PTA people are so much hopeful that these pulsars can give us another window to study the cosmological history. Okay, I have spoken a lot. So now, and of course, the last point is that the physics of accretion can only be studied using these objects. Structure of remnants. See, we don't know anything about the neutron star structure, the how can if on the question that Dibya asked, I'm citing her again and again because the question is very much important. It's coming, and I'm just referencing it back and again. So you see these T-shadow objects. Now these are also important because these should be studied. People are recently trying to study that. There's a Max Planck group who is trying to study, because in this situation, when the common envelope phase is there and phase is just formed, and the Eddington, and the accretion rate is super Eddington, it is very much possible that this white dwarf will not survive, or the neutron star here will not survive the rate of accretion, and it will form a black hole. Okay, and we don't know what exactly will happen. How will the internal structure of the matter change? Okay, and these questions can only be answered if we are able to find out what exactly changes the matter. So yeah, like Luke sir always used to say that we have not yet pointed out any example in which a neutron star has collapsed to a black hole. So yeah, that's a very important statement, because we should. Yeah, it's one of the burning topics. Oh, sorry. Yeah. So now, if people are interested, I'll give a brief overview anyways. So now how do we model them? How do we simulate? How do we connect all the dots and understand that which system has produced which exotic object? So for to answer these questions, we will have to use some modeling tools. So one such very important and very famous these days modeling tool is MESA, and I have been using it for since last summer. it stands for Modules for Experiments in Stellar Astrophysics. It is based on Fortran, and it's a one-dimensional stellar simulation software. So for some of you, it might sound insufficient. Only one-dimensional, why? So there's no answer why. I mean, of course, we want to live in a three-dimensional world. We want to simulate it in a three-dimension. People also want to simulate four-dimension. But see, the number of equations that we have to solve is really becomes, really becomes large. So you use, for example, if we have to model in the, say, the third point here, if we have to model X-ray binary, say a neutron star plus main sequence donor. So the main sequence donor star has to be evolved, okay? All the parameters of evolution should be studied. And then the software should also be able to calculate all the binary parameters, which is being affected once the mass transfer starts. Okay, so this is like a set of 10 differential equations. So solving them, so currently our packages are only able to solve for 1D. Some people have proposed some 2D packages, but they're not yet reliable. Okay, so I think Chandan is developing one 2D package. Okay, anyways, so yeah. So with this overview of MESA, we can, if you guys are, so yeah, this slide actually, I wanted to go to the example, to folder and see things like. So for that, I want to know, it's already 8:30, it's a Saturday evening. So if you guys are interested, I plan to demonstrate. Otherwise, I will just wrap it up in 2-3 minutes, because there is just one slide in which I want to talk about its importance, and then it's over. So yeah, let me know. Should I demonstrate or not? What do you want? Or we can keep a separate session for interested people or whatever. Hello. Hello. Hello, someone respond, please. Hello.
I don't know what's the problem.
Okay, your voice is breaking, Abha, but I get that you are trying to say that you don't know why are others not speaking, right? Okay.
Hello. Yeah, I think that it's pretty late. I think we can have another session where we can demonstrate and go more deep into this.
Okay, so I think then I should just wrap it up. Okay, so the last thing I wanted to talk about is why are such stellar evolution cores important? So why do we need such stellar evolution packages? So yeah, I think I have already answered that question, because we need to evolve so many equations simultaneously. We need to solve so many differential equations together at every step of the evolution. That's why we don't need any a simple code or something. We need a package which can take in all the physics. Okay, so I think I might be able to explain this better if I get some chance to demonstrate how to use MESA. But here are some examples of some hard codes these days. I'm just showing these examples so that students who are there in second and third year, they can try looking up into the details, and of course if they're interested in working in astrophysics and they're working in approaching people for internships and all, then you should try to look into one of these. Say stars, then there is MESA, there is Poseidon, and there is Gyre. Gyre is this stellar evolution code. Stellar oscillation code. Then Poseidon is there for including general relativity effects into MESA. Then MESA is there for all kinds of stellar and binary evolution. Then there is stars. Stars is for stellar evolution, just one star evolution. Okay, so one important point is that once you are aware and you have some experience on working one such stellar evolution code, you can very well contribute in their development, and you can very well choose to develop some other package of your own. Okay, so those are, that's also a possibility. And you can venture into all the subsections of astrophysics. For example, if you know how to use MESA binary, then you can use it to evolve common envelope phases. You can use it to evolve even exoplanet systems, and you can also use it to study the accretion disk properties. So you can also similarly, if you study Poseidon, you can use this code to study different analytical aspects of GW sources, gravitational wave sources. For example, what conditions lead to gravitational wave release when two neutron stars merge? Yeah. So yeah, and most commonly used languages are Python and Fortran. So if you want to work in stellar astrophysics, compact object, high energy astrophysics, you should learn one of them. And they're not, you're already familiar with Python, you must have taken courses, but Fortran is also not difficult. If you're aware of one coding language, you can easily switch on to another. So yeah, had I demonstrated MESA, it would have been fun. I would have been able to answer these questions in a better context. But since we choose to not do that, I'll just tell you the last thing that the most important question that I was asked in so many interviews, even while joining this IMSc here, in the interviews, that have you written any code yourself? Meaning, have you included any physics in the package you are working? So if you simply download and run MESA for a few cases, people are not going to value it. You must write codes to include your own physics, and that will be your contribution. Okay. So yeah, with this message, I would like to end this talk. If people are interested, we can have another talk in which I can explain what I did in my project, how I used MESA and how I used other code packages, etc. Yeah, so if anyone has any question about anything I've spoken wrong or something, please, now is the time to object, ask, or just leave for dinner. Thank you all for attending this.
Hello.
Yeah.
आवाज आ रही? हाँ. So you mentioned कि GW sources को भी जो है क्या कहते हैं देख सकते हैं using MESA.
नहीं, देख नहीं सकते हैं.
मतलब कि you can analyze you can
model कर सकते हैं. Not using MESA. That's why people have developed Poseidon and Gyre. These two codes, Poseidon and Gyre, these are really important. If you want to look into compact objects. In MESA, you can use, for example, Gyre calculates the eigenfrequency, eigenfunctions of the normal oscillations modes of any model. And this is very much important if you are trying to study neutron stars. Okay.
Neutron stars, binary black holes.
Any compact object in a binary system. Then there is this Poseidon. So Poseidon has been, this is population synthesis with detailed binary evolution simulation. So they're like,
They also use MESA, right?
So they are built to be, you can use them independently, but you can club them with MESA.
So Poseidon must be like a package that interfaces with MESA to like model the binary systems for GW analysis.
I'm not sure about that GW analysis, but yes,
okay.
I mean, because see, GW analysis has a lot of part. If you want to include, it can be as less as what I am doing. I have modeled a low mass X-ray binary, and I have included the effect of the torque which is there due to the quadruple moment of the neutron star. So that torque is there because some gravitational wave is actually being produced from the system. So if you want to do simple modifications, you don't need this Poseidon, and you can just do it in MESA itself. For example, there was a recent paper in which, so that was the first attempt to model the time evolution of Thorne-Jacob objects, and that paper was published in July, and people used MESA people just wrote an extra subroutine in MESA to modify gravitational constant G, capital G, according to GR effects. So as simple things can be done in MESA. So the best part about these codes is that you don't have to depend on them completely. You can just take them and you can modify them, include all the physics that you want. That's why these are important.
Okay.
Yeah, so
does anyone else have any questions?
So yeah, here no one has questions. So we should end this. Thank you for the speaker. Amazing talk.
thanks.
Okay.
Bye.
Bye.